So thank you, Sauman, and thank you all the organizers. Uh, yeah, I think this is the first time I'm coming to IIT Madras. So I came once. I was a student. This is the first time, and yeah, the weather is very good here when compared to Indore. That's the first thing I can say. Yeah, because we are frying there. We are 44 every day almost. So I could sleep properly yesterday night. So anyway, thank you. I know Sauman because he was there with me in IIT Indore for maybe 6 months or so. We could not convince him to be there. So he wanted to go away and come to a better place. I hope you are enjoying this and you're doing this wonderful workshop that definitely that will tells a lot. Yeah, so about myself, before I just move on, is I'm Satya Bulusu. I have done my PhD in computational chemistry, so nowhere related to what I'm going to talk now. Under Shao Zheng in Nebraska, then I have done almost 4 postdoctoral positions in US and Canada. Then luckily I got a job in IIT Indore. And then once I joined in IIT Indore, me and there is one more computational faculty who are there, and for good amount of time, there is no theory person. We are just computational chemists. So I thought, okay, fine, I will somehow, that is also pretty vague actually. This person whom you see here, Professor Arup Banerjee, he is the colleague and student of Professor Harbola, who has been dealing with you for now good 2 to 3 lectures. He's his first student and colleague somehow, and he is in RRCAT. Somehow we came to know about each other, and then he started sort of guiding me through COVID days. So why I'm telling you this story is, like you, I'm also new to this topic. Okay, so whatever I learned from him, he is sort of my mentor, and I think I'm more like a student to him, though I use the word collaborator here. So whatever he taught me, it was really I really enjoyed it for the last 2 to 3 years. Of course, we could publish few papers, but mostly the way he was teaching me this, and he has retired, sir. Yeah, he has retired last year. Yeah, a wonderful person and beautiful teacher. I mean, I miss him a lot. We are trying to get him into IIT Indore for some lectures at least. We'll see how it goes. We are starting a BS program now, so we want to get him. But why I want to tell all this is the whole credit goes to this guy teaching people like me who are nowhere related to these. Yeah, that is the issue. So what I heard is Professor Harbola and Arup share. I mean, almost they are in same age, but he's just 1 year junior. But it so happened in their system that he has been his first student. But they're like friends actually. So I met both of them. Yeah, yeah. So very interesting guy, and thanks a lot, Professor Arubda. Because of you, I mean, we are learning, and I'm trying to put something, hopefully. And if you don't understand, don't give me, I mean, don't think twice to give me a call or a message. Or to that extent, even I'll give the email ID of Arubda. He'll be in touch with you. Okay, such a good person. So he doesn't go back. I mean, if he has to talk, then he'll talk over phone and try to somehow convince you with this topic. Okay, so because I was pretty new and to this, so he said, let's start with something very simple, and I think that will really help you guys too. And he said, what are you good at? So I said, I'm a computational chemist. What I'm good at? Doing computations, that's all. Then he said, what else you do? So I was, at that time, I was sort of learning machine learning models. Nowadays, this has become, I mean, very, I don't know, wherever you go, in whichever field you talk, and even my director, to whatever thing you talk, he will introduce AML somewhere or the other. In my IIT, you have AML course in almost every domain. Okay, it has become that important. So anyway, I started this in 2012, working on AML. So he thought, okay, fine, how can we use it to this conceptual DFT? Can we do even that? So he asked me to learn few things, this orbital free DFT and all. And he said, can we use it for kinetic energy functionals? So I said, okay, fine, I don't know anything. I'll read whatever you say. So I read, and using his knowledge and my little experience with ML, we have got some idea. Not really much, as I say, but we have like maybe 2 to 3 papers, one PhD student almost about to graduate. That's up to it. Okay. So anyway, with this background, I want to take it forward. So what I'm going to do today is, it's a pretty long session. I don't know I can take all the 3 hours or not, but I will take the first 1.5 hours, and I'll see if I can give them a Python program or something, if they can work it, do a hands-on. I don't know how it's going to go, but if it all works well, maybe they can run a Python code in the computer. Okay. So with this, let's take it forward. So, sir, I've read a lot of your papers. I don't know I understood or not. Professor Chattaraj, Professor Day, Ghosh, these 3 papers I keep reading a lot whenever we want to optimize, do a CF on this Euler's equation. You guys have done wonderful lot of work. We are doing something on atoms even till today. Those were papers published in 80s. So thank you, sir. Thanks for all that work. Anyway, so I won't even go up to atoms. I'll just go up to a model system. I think that should be good enough for us. If you really want to jump into atoms and all, I think I am there always. I'll give my email address, and you can discuss with me anytime. Okay, so let's start with this now. Kinetic energy functionals and why it is important. So this is an outline. So what I'm going to do is, whenever there is some derivation that is required, I'll try to put it on the board here, and you can. It could be a simple one. It may not be that difficult. But if there is any mistake, I see great professors here who can catch it and point it out to me for sure. So anyway, the contents goes. I'll just take a simple 1D system. No difficulties, nothing much here. Using total kinetic energy and its functional derivative. Okay, so. And then the second thing that I'm going to probably do is a 1D system using polykinetic energy. These are the 2 things that I've learned. So I'll put it. I won't go to the atomic systems at all. So that's the outline as such. So let me. I mean, now I think you have had a lot of courses. I mean, a lot of talks here, and this is the basic equation, right? So energy, what it says, total energy as a functional of density. Okay. Yeah.
Why are you at the very beginning jumping into Coulomb?
Okay. Yeah.
You can start with simple Euler-Lagrange equation where you don't have any orbital picture.
Okay.
So when you talk about kinetic energy functional, what I mean that I don't want non-interactive kinetic energy.
Yeah.
I want to build the kinetic energy of the interactive.
Yes. Just guide me, sir, if I... Yes, that's the basic equation, okay? And then from this equation, this is the basic equation. Why, what sir is saying is, I am trying to get this T into TS. TS means a non-interacting system right away. So, when we start, we have to start something with very basic, okay? Then we have to sort of yes, of course. Yeah. So that's the way to go forward for sure. It's an orbital free, and when it comes to when it comes to TS, then the Coulomb equation will come into picture. Okay, that's the basic equation, and then we have from here what we call as Okay, and that is a basic Euler-Lagrange equation to start with. So we have to use this equation, minimize for the density. Okay, and mu is your chemical potential. This you might have heard till now. Okay, so I mean, I'll just go by the way I have formulated. Then I'll come to this again. Okay, so this T, I mean, this total kinetic energy is a functional of rho. The thing that I've learned here is, if you see V external is the external potential, and V Hartree is your Hartree potential. Okay, if you have two electrons, how they interact with each other. But if you take kinetic energy, this is the total kinetic energy of the system. Okay, so this has a mathematical form, no problem. This has a mathematical form, no problem. But what about T? Does it have a mathematical form by itself? That's the question. If we don't have a mathematical form, then we have to devise a way to get T as a functional of rho, not as a function of orbital. Yeah. So with that, keeping that in mind, the very first thing, I mean, I know Konsham has been discussed a lot here. As the very first thing that they have done is they have sort of taken this total kinetic energy, and I mean, this is a clever way. Now, I don't really have to go into details of Konsham because most of you might be knowing this. They have taken the total kinetic energy, and what they have done, the clever way is they have taken, okay, before we even go to the non-interacting part. Now, this is the basic equation, then this is the Euler equation that we have. I have to solve this somehow, but I don't know the functional form of T. So where I am, somehow I have to solve this without or guessing some functional form of T. So that was in my mind at the time because I am new to this. So what Arup said, okay, fine, take it forward. Get the functional form of T. Somehow get approximate T. So I have to approximate T. How will I do that? And why he is asking me to do that? He said, you are very good in doing ML. So get your ML technique somehow and approximate T.
There are thousands of functions which are in real sense density functions. They are not like non-interacting theoretical system like Bulusu.
Yeah.
The first one, let's say, is the Thomas function.
Yes.
So you can write kinetic energy as a true density function.
Yes.
Then you can have a gradient expansion.
Yes.
So you can get T0 plus T2.
Yes.
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 So in principle, you can get
You can get the functional. Yeah, I think.
No orbital, nothing. And many people long ago have solved the corresponding orbital equations also.
Yes.
Very good results.
Yes. I say I can show you few of them. Actually, I have that in the later pictures. Oh yeah, I can show you actually because you have raised this point. I'll go back again just for the sake of argument. I will do all this again. So yeah, I mean this one I got it from Professor Nicholas Handy's paper in 2001. And here these are my local functionals. I'm sorry, I'm jumping few slides. I'll come back because sir has raised this question. So I just want to put this. And this is the Thomas Fermi. Now, why he says Thomas Fermi? Thomas Fermi is TF can be completely written as, right? Okay, it can be completely written as a functional of density. Okay, so if it is homogeneous electron gas, this is very much valid, no problem. And people have worked on this. I think long before Kohn-Sham equations and Hanbok-Kohn theorem has developed, I think this has come into picture. So that's really remarkable. Now, how to use it? What people have done is, I mean, because this was developed, just guide me if I'm wrong. Just because it has been developed for a homogeneous gas, that Hornberg and Kohn has developed their model based on homogeneous gas. Is that true?
No. Bicycle in homogeneity correction, you can see 1/5 bicycle.
Yes. Yeah.
And Dirac exchange also I can see.
Yes.
Okay. Unfortunately, no one took the name of Dirac here.
Yeah.
People are talking about Doctor.
Yeah.
Someone is saying later, someone is saying LDA, but it was Dirac.
Yeah. So,
1/5, remember, so if you go for the gradient expansion, that is 1/9 bicycle. But you know that if you want to solve the Euler equation, you have to take 1/5, and that was shown by Yoni and Thompson.
yeah. So,
1/8 is bizarre. 1/8 is bicycle.
No, 1/8 will come with bicycle. In addition to that, you have to have 1/9 of bicycle. So 1/72. That is if you put some density and try to generate kinetic energy. But if you want to get good quality density solving this, then you have to take 1/5 of bicycle. That was shown long ago before when we were computing. This is totally density.
yeah. So this total energy can be sort of decomposed. No, first we'll just talk about Thomas Fermi. You can see the Thomas Fermi's energies here for atoms. Okay, these are the atoms. And why I'm jumping this to say, and you have HF or even to that a KS, whatever. Yeah, that's what it says, 1/5 or 1/9. Yes. So if you see this, and you have many variants of TF here, TFD, that is Thomas Fermi Dirac. Thomas Fermi Dirac 1/9 of W, that's what he's saying. And Thomas Fermi 1/5 of W, and lambda is equal to 1. Thomas Fermi Dirac and lambda is equal to 1. And then you have your sort of exact Hartree-Fock, if you think so. Then they are sort of comparing it, and you can see these are way off mostly in these numbers. That's what I can see in that. Okay, that is the only take home here, not much as such. And when I go to the next one, one interesting thing that you see is in HF, if you see all this density, I mean radial density, of course, with respect to R, when you plot this, for HF, you can see this shell-like structure. And for all the other functionals that you have, they don't have this shell-like structure. So that is one of the motivation for all of us to develop these functionals. Okay, you have to have this shell-like structure, whether it is KS or HF. This all comes with this shell-like structure. So again, sorry, I'm just running because he just raised the topic, so I just wanted to. Oops. Okay, so we have some functionals, whether the functional is dependent on rho or whether the functional is dependent on rho, comma, gradient of rho or higher order gradient of. We have some functionals, but the problem is this. So we have to at that time. Then why is this kinetic energy very important? Why it is very important? We all know now how exchange correlation is so important for chemical binding. Why is kinetic energy very important? Why we need to know? Because see, energy is decomposed into kinetic energy and the potential energy. We have different parts of potential energy. Why is kinetic energy so important?
My very first paper came in 1980. The title was Role of Kinetic Energy in Density Functional. And there I review whatever kinetic energy functionals are known.
And just.
So
what is which year, sir? 19?
I'm giving.
Okay, thank you.
The title was Role of Kinetic Energy in Density.
Okay. So, I mean, anyway, why is kinetic energy? I don't know anything. I don't know much of chemistry. I mean, I know only chemistry. I don't know physics part of it. But why is kinetic energy so important? Any idea? Why should I model kinetic? Anyway, one good thing is it doesn't have a mathematical form. That's anyway. But what else? What else could be the reason? Understand the dynamics. Okay, but I mean, for the dynamics, you need the interactions too, of course. So you have done any DFT calculations? You might have done a lot. So you can break the total energy into the contributions from kinetic and the potential. Okay, the major part of the total energy is your kinetic energy. Major part of total energy. Okay, so let's say I am approximating a functional for a DFT, and I am not touching kinetic energy. Okay, I am trying to implement good functionals for exchange correlation and all, but I am not even touching kinetic energy, which is the major contributor to the total energy. Okay, rest of the energies are very small. So that is one of the reasons that is a reason it plays very huge role in understanding and developing these functionals. Okay, it's a major contribution to the total energy, but it doesn't have a mathematical form. Then, of course, Hornberg-Kohn and Kohn-Sham has come into picture, and you know the story. I don't want to go in detail. And my first equation has come into picture. They made this total kinetic energy into the non-interacting part, and the leftover is put into this EXE. Okay, and they said, okay, whatever you want to do, this EXE, you develop the functionals, you approximate it, do whatever you want, but I have a simple non-interacting part. And that non-interacting part, they smartly used what we call as auxiliary orbitals. Okay, so right now, before we go further, one question that I want to ask, because you might have now experienced Kohn-Sham a lot in discussions. You have your Kohn-Sham theory, okay, that is this equation, and you have Hartree-Fock theory. What is the difference between these two? Okay, so Kohn-Sham is based upon density. Okay, so let me write it down here. I think this becomes a bit important for us. So HF, it's based on your wave function. Okay, so you will be solving this is the equation that you will be solving, right? Okay, for the Hartree-Fock. And this you guess from the stated determinant. What happens in Kohn-Sham? Kohn-Sham looks the same actually, if you see. I'll just put as Vs here. I'll just put this as pi I. This is a single orbital picture of Kohn-Sham, right? Now this is using the orbitals pi I here, and there they are using psi I. That is the only difference if I write these two equations. Now where is the difference? Where is the density coming into picture here? Because if you have to understand DFT, first we need to know what is happening in Hartree-Fock. So that is something, you understand my question? Okay, so where exactly these two differ. As she said very well, it is the density functional theory. Kohn-Sham comes from density functional theory. But we have what we call as auxiliary non-interacting orbitals. Is this the same as your Hartree-Fock? Or is there any difference there? Okay, where is correlation? Okay, there is correlation there, of course. Okay, in Hartree-Fock you have only exchange. Okay, that is one of the difference. The main difference is if it is DFT, I want density. I don't want orbital at all. Okay, it has to be dealing with density. So how is density coming into picture? So if you suppose that is, I mean, you understand my question?
Is it somehow right phi a square equal to
Oh yeah, that is the way we are defining the density, of course. But how is density to see? What is the initial guess for Hartree-Fock? You get a slated determinant, and you will be solving this single orbital equations. Okay, that is the way. Okay, then in this V effective whatever you have your exchange, you have your J, I mean the Coulomb. Okay, and also the external potential. All these are there here. And if you go back, if you go to Kohn-Sham, actually it is the same, right? You have your external potential, you have your Hartree, and you have Vxc. As he said, you have both Xc there somehow. But what is the main difference then? My initial guess should be density somewhere. Right, sir? My initial guess should be density for density functional theory. My initial guess should be orbital for HF.
Beginning the construction of the operator. Operator there, some operator over here. Here you require the operators. Here you require the density.
Yeah.
To solve this, you have to get the operator. Operator get some.
Yes.
This ES, when you construct, it is as a density function, not as an orbital. But if you see the corresponding Hartree-Fock one, exchange gets it, we are writing basically the form of the orbital. Okay. So how you get it with some initial guess of phi I, you can simply someone is telling phi I mod square some over this. You get automatically that. With that density, you can simply construct the corresponding from the exchange position, whatever form you are taking. And then you solve it. So density comes straight away.
Yeah. So the operator here, as he said, and that's rightly mentioned. So that's we have to know. Here we don't have anything like that. We are it's a iterative process, SCF process. We are starting with some orbital slated determinant.
How many of you have written anytime, any code for solving either of them or both of them, or you have always used some software to run Hartree-Fock? If you have written code yourself, you will know ins and outs of it. That is very fast thing. You have to learn how to write the code.
Yeah. So here, when you talk of Hartree-Fock and any of the codes that you take, you will take a slated determinant. Then you will be solving with this one electron Fock operator using one electron this equation. Now coming to DFT, it won't work like this. Of course, you have the auxiliary orbitals that is there, but most important, how to get this Vs. This Vs, the operator that sir is mentioning, is coming by assuming some initial density. Once you guessed Vs, then you are using this non-interacting orbitals, and in the same way as the Fock operator, you are doing an SCF cycle here. Okay, the only thing is here my pi star pi, that should summation of pi star pi, that should match with the density. Here my summation of pi star pi should be what in Hartree-Fock? Integral of pi star pi क्या होगा Hartree-Fock में? Should normalize to what? Should normalize to n or to 1? 1. That is the difference. Okay? So that's why we call these orbitals, these are auxiliary orbitals, these are Kohn-Sham orbitals. These are not real orbitals. Because what we are actually guessing is the density. You are starting with the density, of course, and you are predicting this. You are solving this, you will get a good pi. Do a pi star pi, you will be getting the density. You match this density with the initial density that you started with. And that's how the process goes. Is this clear? Okay, that's why Kohn-Sham is a density function, because you start, the iteration starts assuming some initial density. Okay? So that is a basic difference. Anyway, of course, I'm sort of digressing from the main topic here, but let's go to this Kohn-Sham equation, and you might be well knowing about this. And then, yeah. I keep doing that. Arup is good with N because he's a physicist, and I'm good with rho because I'm a chemist. I'm telling you, actually physicists use rho, chemists use N. Just because he wants to teach me, he used N. Is that so? Okay, he fooled me. Yeah. Sir, I merged everything. But anyway, yeah, this is a good question. I mean, till now what I thought is I like writing rho, so I love to write rho everywhere. But then he used to write N everywhere. Then he said, okay, he thinks I'm a chemist, I don't know much, so he'll write N for me so that I can understand. Now I know that what he's doing is for his comfort. Anyway, yeah, we can interchangeably use this, but yeah, stick to one. Okay? Here I keep writing, many times I keep writing rho. Yeah. Yeah, of course. So yeah, let's go one slide further. So yeah, this is the total functional that I have. It's okay, right? I mean, it's just the functional of density, nothing else. Okay, and then well, I can abbreviate with these functionals V external, VH, and VXC, and then I'm just left out with this functional derivative of non-interacting kinetic energy. Nothing else. That is my functional derivative of total energy with respect to N. Okay. So yeah, I mean, the problem is, even if I write in this way, my problem is these two are unknown. You might be knowing by now all this. Ts as a function of N is something, of course, Kohn-Sham has done it in terms of orbitals, but Ts as a function of N is still what we want to somehow guess, approximate. And that's where he said, okay, fine. And then the good thing is, once, again, small amount of digression here. This Ts of N is there. Why I did not start with T? I could have started with T, but why it has to come to Ts? That was the initial plan. And then he said, you are doing machine learning, because he knows he could understand the machine learning part too. You need something for reference. Okay.
It's like a question, obviously anyone will ask that. Anyway, if you are approximating the kinetic energy functional with the density function, why do you want to go to a non-interacting system? You can have but the thing is, people wanted to exploit the known knowledge of exchange correlation.
Yes. That's yeah. Yes.
If you want to make use of that, you have to go back to non-interacting.
Yes.
Because we always published papers on interacting kinetic energy. There is nothing wrong. But only
because we have a vast knowledge of XC. Why don't we use XC?
Yes.
Yeah. Yeah, and because finally we have to see if you are approximating TS, finally we want to get total energy. I mean, that is the ultimate thing.
There is a question also here. The exchange there is different from exchange in Hatripa. Correlation there is different from correlation post Hatripa. Now the correlation with interacting kinetic energy is different from correlation in non-interacting kinetic energy. That you have to see, because if T minus Ts,
Yes.
which you are adding, that is only within the orbital picture.
Yeah.
If you take approximately this your kinetic energy, interacting kinetic energy, that component will not be there.
Yes.
So you have to be careful. Don't take blindly any exchange solution. You have to take this belief is that no. So if you don't know what you are doing, you will get wrong.
Yes. That's an important point. Very important point, and why it comes so important is when I was doing my computational chemistry those days, I used to, for gold clusters, I used to do a lot, and I used to use PBE and B3LIP without even understanding what it is. And B3LIP used to be good results because I used to have an experimental collaborator, and my X-ray photoelectron spectroscopy results that we used to do with Koopman's theorem, it used to work wonderfully well, and we published great papers and all that without even understanding what is really behind this PBE and B3LIP. Okay, and B3LIP never worked. Yeah, and I published, sir, so many papers which got a good job also. But with that, but the problem is I never understood what is. That's why for the students this is very important. When you try to use these EXCs, be very careful. You have to understand. I think a lot of talks have been devoted on this, so I think you go back and try to, especially when you are doing computational chemistry, this is something very important. Okay, and PBA works very well for gold cluster. Don't ask me why. Okay, it works very well. Okay, it gives it gives again. Yesterday I was talking to him, and yeah, he was Chaitanya was telling me that I mean, again, sorry for digressing again. You have a planar gold cluster like 20 AU20, maybe more. Some of you might know this 20 comes with a beautiful tetrahedral picture, and there is a planar model for also that, and DFT usually likes planar, but only with PBE exchange correlation we get this beautiful, very low energy. Very low means I can even go up to 1 electron level lower. Yes, Arup, yeah. Yes. And it is 1 electron, a huge difference. But then DFT with a change in correlation, EXE can give anything. So we have to be very careful there. Okay, but I used to like PBE because it worked for me. I used to get results, then I published good papers. Anyway, so with this, because as he said, yes, that's the main reason people have the vast knowledge of EXE. Okay, and then TS is one thing. The reference comes from my Konsham, so I don't have any problem if I want to do something like this machine learning. So let's again give some idea. I mean, because nowadays it's all machine learning, so I want to put some effort in making you understand what it is exactly, because finally I want to deal with that. Okay, so machine learning. Anybody understands what it is here? Audience? Anybody has done some AML something? Yes, please.
It will give that in 1 year. If you use ML, it will you will get the same result with slightly error within 2 to 3 days.
Okay. So a few things in what he said is he said directly something like neural network, NN. Okay, he used this word, but the basic, I mean, the whole thing comes to what we call as ML. Machine learning. The name itself says machine is learning. I am not doing any learning. Machine is learning. That's why it's it's a subset of AI, artificial intelligence. Okay, and all these abbreviations that comes are here. NN, you see a lot of literature in this now in this decade in 2020. It's huge amount of literature. Almost everybody in computational chemistry nowadays, any other paper works on somehow, somewhere or they keep saying NN, or they keep saying kernel ridge regression. So kernel ridge regression, okay, and there are many, of course, something like any other model that you can recollect. NN, KRR. I mean, NN is widely used, most widely used. Okay, kernel ridge regression. These are regression methods, sort of. So in that way, actually, when I was telling Arup about this, he said, "ये तो क्या है? ये तो parameter optimization है. That means you are only doing linear regression. उसमें क्या है? I mean, you go to Python, you work on it. There are tons of way you can do a regression. So this is one of them. Yes. Yes. Yeah, many soft computing methods have come into, yeah. So yes, these things do work very well, but it has, there is some concept. It's just not regression. There is huge amount of concept behind it, especially the neural network. So I'll put some effort for you to understand what is neural network. Okay, so I won't give details of it. There is no need of that, because yes, I will tell them. Yes, I will tell them. Yeah. So in ML methods, ML means machine learning. Machine will learn. Now you may say, what really is machine learning? Machine is learning something, and whenever you want something, it has to help you to answer the question. That means we all know, for example, Schrodinger equation is something very difficult to solve. Let's say, if you want to make the machine learn, once the machine has learned what it has to learn, then you don't really have to always solve it. Machine will do it for you much quickly using some empirical parameters. That is very close to your real ab initio picture. I mean, that's what is machine learning all about. So for example, you keep doing whatever, when in the computational chemistry lab, what you do, you go do an optimization, do a energy calculation, and as soon as the size of your chemistry increases, size of your molecule increases, what is happening? It goes, this goes to n cube. Okay, that is a scaling, right? And then for really proper experimental system that you want to really work on, even for me, doing a 55 atom gold cluster was very difficult. Getting a potential energy surface of that is very difficult. It's been challenging. Okay, these challenges to overcome, the way around is, one of the way around is, if you can construct machine learning paths. Okay, so once you construct that, you can use it, and as a, for example, you are running a classical molecular dynamics. Okay, and that means classical molecular dynamics, the potential is just a classical potential, whatever be the potential, classical potential. Okay, result may not be the same as your ab initio, but if you really make sure you learn it properly using a machine learning model, you run a machine learning based molecular dynamics, what you get is the speed of this classical model with the accuracy of ab initio. Oh yeah, then that's it. I mean, computational chemistry can be completely easily can be used on a laptop or a single PC then, or maybe a bunch of few computers. It's over. Okay, but this has its own problems. Okay, you cannot directly think, okay, fine, I have made a machine learning potential, I can get whatever I want. It has its own drawbacks. So again, whatever we do, of course, this is still in a research phase. Though I think Chaitanya was telling me that there are a lot of databases right now for material data. What was that? MAs. Yeah. for catalysis. These things have already come up. I don't know, most of you guys are using all this, but transferability is a problem. That means chemistry all goes with transferability from one system to other system. Is it transferable? You have to be very careful, because did it learn? And that's where when he says supervised learning, it will come. I'll try to put it on the board. Okay, it's an open catalyst project, and there are databases that are already optimized. Okay, you can use that and you can quickly run a molecular dynamic simulation with this machine learning potential. No problem with that. Okay? But it has its own problem. One is transferability. Transferability because not the size transferability, but let's say you have two different atoms that are not in the training database, then you won't get the results. The next very important thing that chemistry is lacking is reactions. All this works very well when there is no reactions. As soon as you have bond breaking and forming, machine learning models, I don't know if anybody has any idea, you can educate me, but as much as I know, these machine learning models really are not up to the mark for bond breaking chemical reactions yet. Okay, there are few already, but these, again, it becomes very expensive to do a proper training for creating such kind of models. So, jumping into this ML models, there are three kinds. One is what he said is supervised. The second one is unsupervised. Is there anything else? I think these two are good enough. Yeah, there could be semi-supervised. I am not much used to this semi-supervised. Okay. Okay. So. That's a beautiful analogy. Yeah, but just the name, looking at the name students, what you can think about it? He already gave the answer for you. Supervised, unsupervised, semi-supervised. Supervised means the machine requires, the training requires training. Yeah. No, but now the papers have come. People are, and we are working on it. People are doing a beautiful unsupervised way of solving the Schrodinger equation. Pattern recognition. So it will go in such a way. There is no supervision. You just give it. You just guess the orbital, give it. It will by itself. But all the orthogonality, normalization, all these things has to be properly given in the equation. Then it can be done. So supervised is, as he said, yes, somebody is supervising. So what is supervising? For example, I want to reproduce Kohn-Sham energies. Okay, Kohn-Sham computational data is there with me. So I'm using that as a reference for this so-called an empirical equation that I have that is coming from my neural network. Let's say I'm using neural network. Okay, I have some sort of empirical equation. Empirical equation means the equation that comes with various parameters that I have to optimize. Okay, these are optimized in such a way that the difference, the error between the predicted from the neural network and the one with the DFT is very small. So it is an iterative way. That is the way the supervised works. So here in this, for this, I won't go with unsupervised, we will only touch the supervised. Okay? And then once we know this, we will see what is this NN, neural network. Any idea from the audience? What is neural network? So basically, how the neurons work in our system, human brain. That's all. Okay, these are the signals. Okay, only thing what people have done is they have taken this model, this analogy, and using bunch of mathematical equations, they mimicked. And finally, they are trying to understand the system I'm making the system intelligent with these neurons. So if you see most of the papers nowadays they don't even, in chemistry papers, they don't even give the architecture, but I think it's better to know the architecture, what an ML, usually a neural network has by itself is two things: your inputs, usually they describe with this circular things, these are called nodes or neurons, okay, and that is the inputs, and then you have one or more output. Okay, so what basically we are doing is mapping these inputs to the output, and that's what we are doing, nothing else. We are mapping somehow.
And your computer is analog. You put some A into it. It's
Oh.
artificial.
Yes. Yes. So literature has come to an extent. Earlier I used to use A, but it is so now people forgot using human brain. It's all accepted, everything is artificial here.
Because of the advent of ChatGPT.
Yes.
They're behaving like
Yeah. So nowadays, yeah, that's what I see the literature. Literature says, theek hai, I mean, there is no need of A, it's already assumed. So people just say neural network, NN. Okay. Or to that extent, they use NN, they'll say machine learning. Okay, it has become a very generalized word. Anyway, so what it says is you give bunch of inputs, okay, whatever be the inputs, let's say it's a density as input, you give bunch of inputs as the density, and your kinetic energy is output, that is your output. Now you have to map this to that. What do you mean by mapping? Somehow this has to transform in some way magically and give this number. Some number is coming out, okay? And then I have my T cone sham, and that is this reference that is sitting there, that is guiding this. Okay, so the way I'm going to map, okay, this is guided by this. That's why it is called supervised. Okay, so to give what is here, that is a backbone. Okay, what do we have is the input layer and output layer, and in between what we call as a real computer that is working behind. Okay, and then we have in that real computer, the way that I am going to put it is through circles. These are empirical, that means number of, these are all variables. There can be many layers, 2 layers, 3 layers, any number, and this is my computer that is sitting there. So this information is passed to computer, that computer is doing something, it is spitting out some number. Okay? Now, so the way, if you think, as your brain goes, all this somehow should be connected. There should be some connection. That's how you can pass the information from one place to other. So these are all connected. And they are connected in a many-to-many fashion. Okay, everything is connected to every neuron. And then all these neurons are connected. Okay, and then all these are connected. So this is a way things are connected, and your information has been transmitted from one layer to other, getting processed in such a way that finally whatever you are getting is something completely different from your input. So it is not a direct mapping, but it is mapping through a computer. Okay, the most important thing is, sir, when you write these lines, what really is happening here? What really is happening? You are taking some information. So usually this is all done in the computer, right? And computer is taking only numbers, right? So some numbers are given. Let's say for our for our discussion, these are some sort of representation of your density, electron density. Okay, this density has to be mapped to your Ks through this. So these numbers are somehow going into each circle in some way, and then it is getting transformed in the next layer. You may ask how many layers should be there. These are all variables. It could be 1 layer, 2 layers. How many circles should be there? Again, variables. You have to check trial and error. These are these number of layers and number of neurons in each layer. All these are variables. You have to do a trial and error check properly. Then you can optimize this. And when I draw a line, what it means is there is some what we call a weight associated with this line. Okay, this weight, this is my real variable that I am going to use. So if it is the first one here, usually it goes by W11. Okay, in this way, if suppose, this will be W1, 2, 1 refers to this one, 2 refers to the next one. In this way, we can get all the weights, unique weights that represents the connections. Okay. Then what is happening here? Processing. That means this is my CPU, right? Central processing unit. So each circle is getting processed here somehow. What it is processing? It is taking information. These two, very simple. Actually, if you can think about it, it is not doing a big deal here. What it is doing, it is taking the information here. Okay. It is adding all the informations from everyone. How it is adding? By a weighted average. So it is weighing it and putting that information, and it is summing here. Yes. And once it is summed, that is a linear way. You need to, because real world is non-linear. So somehow you are doing a non-linear, you are introducing a non-linearity here. How you are introducing a non-linear? There are many ways to do it. People use tan H functions or sigmoid functions, which are really good. Sigmoid functions goes by 1 plus e raised to the power of minus x. Okay. Good thing is if you differentiate, it will be much easier to tackle this. Okay. So this x, whatever I am writing here, comes from here. So this is the way you have non-linear. Non-linear क्यों करना है? Linear fashion. This world is not made for linear. It has to be non-linear. So we have to get this non-linearity imbibed somewhere, and that's where we have non-linearity. Once we have non-linearity, of course we have weights again. It is processed to the next layer, and finally it comes. It throws some number out. Okay, and this number, whatever it throws out, is being guided with the reference data that you already have with you. And what are the parameters when it is guiding these two? When these two are guided, what is happening? The weights here are getting optimized. I hope you have some understanding of this. So you have the inputs, some representations of densities, and you have the output, that is my kinetic energy, let's say some number, and that is guided by the real kinetic energy. So there is an error between them. My whole idea is to minimize the error, right? How I am going to minimize the error? By changing these variables. Okay, and this kind of network, very well used. People don't even talk about the complete name. It's called feed forward. Okay, you start from here. This is the forward direction. You are feeding the inputs in the forward direction. It's called feed forward neural network. Of course, you have some bias. Okay, bias will control this number, because the number can be anything that is spitting out. So you have to control, get it close to the TKS. That bias will take care.
Weights and bias, they are coming because you are basically trying to simulate the human brain. So every day we are getting many information from many different places. So how much weightage shall I give to which information? That is coming from the weight. And there are certain bias, inbuilt bias. Like suppose I am saying something political, etc. Maybe someone else may be interested. My bias will tell, forget about it. This is not any kind of information. So that is the bias. So immediately I say to bias that these information are not allowed to enter into my question. That is the bias I have to put deliver. And some of the information are more important than the others. So that comes to the weights.
So that comes to the weight through your inputs. So which you want to transform. Because suppose
input is whatever the information you are trying to put into, that is coming, and that is like information what is floating around, they are entering into the brain. But your brain deliberately will tell that don't take all the information.
yeah. You have to selectively, that's why you keep adding it. You have to selectively take the information. Yeah. You have to selectively take the information. That's where these weights are important. How selectively, how much of this component is actually reflecting here.
No, there is very important thing. Suppose someone is working with AI. Obviously, that person will be much more interested in the top where AI level is this. Okay, that tells you that information with very heavy weight will come. So you want to get that information more. Okay, others passing by. So some of the information you don't want to enter into it. There's a bias.
I think beautiful analogy, sir. Thank you. That's a good thing. Yeah. Yeah. So
It is better for the completeness to put some bias with some error.
I'll just put index here. Now, when I put this arrow like this, it doesn't go to only this, actually, it goes to all the nodes. Okay? So, it looks like, your equation looks like Wij, okay, times your input, let's say that is AI, that is your input, plus your bias, so Bj. It looks like this. That is the information that is going inside here. Okay, and this information is being non-linearized in this type. So this x is, let's say this is your x, and this is the way it is non-linearized. This is the way it is moving forward. Okay, and that's what when you like, because at one point of time, I think you will be most of you will be using Python packages. They are already there. And it is not that difficult nowadays to use machine learning algorithms. Earlier when I started, we have to hard code everything. Right now, it is there. Okay. So for the people who want to start this topic, you just go to Python, few tutorials, and it is not that difficult. You can use it. Okay, you don't really have to do a hard coding here. I'll tell you what is the problem. The problem is, whatever I'm writing here is very small. You really want to construct a neural network, this will be, let's say you have density here, talking about real atoms and molecules. These values can be huge. This can go, could be, let's say 200 numbers. And these values will be huge enough. So, not worried about these numbers. What I am worried is this connection weights. That will go exponentially more. And you have to optimize many. How will you optimize so many? That's a big, in the weight space, it's weight space. When I was using, again, I'll just go to the gold cluster. When I was doing AU20 and all, I used to have a weight space of 2000 by 2000 matrix. And that kind of matrix I used to optimize. Now, to optimize that, generally people use a steeped descent method or something. That is there, well known. But that may not, because then it, as usual, the problems with potential energy surface, it will stuck at some local minima. It will don't take you to the global minimum because you are talking about a weight space of 2000 by 2000. Then you have to go for a second order differential. Okay, and that will be more expensive. These, yeah, now the soft computing techniques have come a lot here. Yeah. So many things are there, but optimizing this itself is a headache. But usually deterministic methods usually work very well here. With my experience, I can tell you. So you can use this second order differential equation, solving the matrix, Hessian matrix and all, and it works very well. But it comes with the price that you have to pay. That is a computational expense.
once you write it, throughout your life you never how to use. Writing program is very good exercise. Python, Java, C, program, whatever language you have, language is not.
Yeah, I think, yeah. So you use interactive Python, Jupyter Notebook. I think that's the best. I think that's the best thing. Interactive Python. You don't really have to remember many things here. Don't do Python by step by step. Nowadays things have moved so far. It's easy for you to code. But don't use ChatGPT, please. As soon as it can give you some code, but don't do that.
It is not at all wise to blindly rely on someone else's. You will never learn.
Your major aim here is you have the quantum energy. You wanted quantum kinetic energy.
Yes.
You wanted to learn the true kinetic energy.
Yes. Yes. I want to learn the quantum kinetic energy. Yes. No true. My reference is quantum. So maximum this number that will take you is very close to quantum. Okay, and that is my exact kinetic energy that I believe, because that is my teacher. I cannot go beyond my teacher.
Actually, what you can do for a simple system, generally they must belong to some kind of set. You just simply you have the input, the density, you have the corresponding, let's say, some energy. You create a model with your omega and say E, all those. Try to see how much are the values of the quantum. You go backward, change the weights and biases so that ultimately you get the reasonable values of pKs coming from your input and the given set of biases. This is your ANN model fixed. Now you apply it to some other system with the same model.
Yes.
And with the density, now you will get immediately the density because the model is there already. This is your ANN model.
So the whole.
Supervised before with some known system.
So I mean that's the next thing that we have to come. Till now, what we are telling what I am trying to tell is how far this is coming close to this. But what is the use of that? See, what is the use of doing all this? Why? Because for the known systems, let's say these are easier systems. Let's say, just to understand, don't even take this as a quantum. Take something, some reference, some teacher, and something easy that I know. Once I get this is my classical potential now. Let's say I want to do a molecular dynamics that you guys do it. Then this is my classical potential now. I can use this potential and run the new system. Now, the question here is that the new system, whatever I do, should not be far away from what I trained. Now, that is the limitation here. Okay, so new system, suppose the new system is far away, that means you add atoms that are not there in the training, it will never give you anything. That is the problem. You do all this hard work, finally it is not so much transferable. That is the limitation outside I want to put it. You have to be very careful here. Yeah, so that is a problem. Okay, now you are smartly, now the smartness comes when you smartly use your inputs in such a way that you can get lot of information, then you can use this model here and there for whatever you want. Okay, so that's the background, but people are working on it. As you said, databases are coming on it. So things are working, and right now there are good number of groups in density functional, Kiran Burke and all. They are working on this kinetic energy functionals. They started with exchange correlation. Yes, and
small question here is so can we use, for example, for simple atoms, we all know we can perform to CCSDT level of calculations.
Yes.
From there you can get true wave function, therefore you should be able to get true density as well.
Yes.
Can we use this information in order to train and learn the functional forms, because there are ways to even use the ML models not only to just get the prediction of the kinetic energy or something, but we can even generate formulas, is what I remember.
Yes.
Right?
Yes.
So, are there any earlier studies which try to predict the functional form, at least for the atomic systems?
What you're talking about, given the construction of change pollution potential, but these days, machine based these exchange potential there are several jobs.
They have already started in,
my
yeah.
question is not about the final, but I'm interested in the form because we do not know what is T of n. The exact functional form of T of n is not known. Therefore, we are approximating.
No, I understand your question. You said, can I dignifiedly get a mathematical form to it, an analytical form to it? Now, analytic.
Similar to how we got the Thomas Fermi, which is not correct, but can we try that based on the densities that we
That's a very good question. That I, as far as I know, the functional form is the one that I'm going to show you right now. That is the neural network form right now. Till now, I haven't seen. Yes, you can get the the functional derivatives properly. You can get the energies properly. All these can be done, but getting a functional form, yes, it can be. But till now, I did not see any paper as such. But it's a
you want to get a function.
this is a curve fitting, but now when you go to take it to the next level and can I design a functional form? Yes, why can't? Maybe we can do that. As of now,
that would be more useful, right? Like at the later stage also, once we have it, then it's like an analytical form is the best thing that we.
Yeah, I think we'll take it to question.
So right now, like we are trying to use this neural network model as a function approximate.
Yes.
So because it's a neural network model, we are not able to get functional form models that serves as a functional form. Is it true?
See, again, neural.
There are two different things. Like when you do any kind of numerical problem, say suppose you have to take derivative of something, but you are getting functions from the nodes. How do you take the derivative? You apply finite difference approximation or something. You cannot take the derivative in the regular sense because you don't have the functional form. So if you want to do that, first you feed it to a functional form and then take the ordinary derivative and like differential calculus. But in this case, you are getting a numerical form of the product. Okay. So if you want to get a functional form, you have to do a class feeding. You have to create a function which fits into the function.
But yeah, but as we know these curves.
Is it possible that the
Yes.
function is so non-local
Yeah.
that it is very difficult to find the function?
In general, it's very
Yes. I mean, talk about kinetic energy. It's not quadratic anyway. It's very difficult to get kinetic energy itself. Exchange correlation, yes. No, function. If you have functional, well and good. I can take the analytical derivative. But here also you can take the derivative, numerical derivatives.
when you enter into the computer, forget about analytical method. It's a digital computer. You have to talk about numbers. If you want to talk about a functional form, then again you have to feed somewhere and go back.
No.
It's a very simple thing. If I ask you what is a plus b whole square, you ask the computer, it will never be able to tell you that it is a square plus 2 plus b square. You have to tell what is a some number, what is b some number, then a plus b whole square, it will give you back a number. Okay. Then you have to do something. The first thing is to do it equally.
No, that's my question. Why do you want functional form? Let's say.
One possible answer is like
Yeah.
nowadays, apart from the normal finite difference and other things, apart from the finite difference methods, now we have this automated differential.
Yes, automated. Yes.
So that means that we will get as good as the analytical derivatives. So at least if I know the functional form, I don't need to do further approximation. I don't need to be worried about my grid, right? For example, in Gaussian or something, how well my grid is there, that better my answer is. But once I have a functional form, I don't need to worry about it. I can have, if there is a need for.
But here I can with.
You are approximating. Whether you are approximating in the derivative state or you are approximating in the confidence. So the problem comes between the trade-off. So in general, it is so non-local as is pointed out. Fitting is not a good exercise.
Yeah, and you can get the normal derivatives and all. Though you are approximating, let's say energy here, you can get the functional derivative from here.
You can talk about those equations, beautiful equations you have written. But at the end of the day, we won't see those equations when you enter into the computer. We see only the numbers.
Yeah. Any other questions here?
So you were telling that like you can get the functional derivatives of the output reducer.
Yes, yes.
I would like to know like if there is any mathematical like an overview of that math
No,
algorithm.
there is a way. I mean, I will show you quickly. You can get the functional derivative of this. It's a simple chain rule. We can get that. But I mean, I don't know. I'm taking so much time with just introducing this topic to you guys. Maybe I don't even will have time for anything else. But I will show you when I go to the models. One thing that we will do is what I think Kiran Burke and all, what the problem they faced it. Let's say they got the energy, kinetic energy, then they want to derive get the functional derivative of that. That is extremely difficult to manage. It will go here and there completely, numerically highly unstable. Okay, so what we have done, I think I feel I will go to that slides too. What we have done, me and Arup are sitting, what to do with this, what we suggest, if there is a way to get the potential directly and then go back in reverse to get the energy. So integrate to get that.
Again, if you do computation using numerical analysis, you will find one important thing: the best possible smooth operation. Numerical operation is the numerical process. So integration can be obtained very well using numerical techniques. The worst thing is the difference. You have to find out any derivative using numerical methods. You will get the worst possible.
Yeah, so that means
you get your potential, integrate to get back the
so these two are the quantities, right? These two are the quantities. So right now I just want to introduce to you how we started. We want to get this out of neural network and mathematically with this get this. This becomes this will not fetch you results properly, but instead you directly try to get this and you integrate this to get this. This is a much easier way. So you learn this somehow, if you know how to learn this, and then you go backwards. Now, if you have your equations, as he said, that will help me in guiding from here to here. Then I'm really good. Okay, so at least one of the model systems that we tried to do, the polypotential that I'm going to show, because this whole problem with Karen Bock's work is, I mean, they mentioned by themselves, is getting the functional derivative. Finally, we have to get the functional derivative because we have to minimize the energy. Finally, that is the ultimate truth. But then, if the functional derivative itself is numerically unstable, then where will I go? Yes, yes. It's this is easy, and because I know this, nah? Actually, it's my. I mean, if it is non-interacting, I don't want to do all that. Then this is. I think I'm doing the signs right. This is plus mu minus, right? And then we can get this. Not a problem at all. So once you get this, then I have, see, this problem again, I used to have even when I was doing materials. Okay, there also the problem is same. The problem is if I want to get the energy and I mean finally I want to get the force. I want to do classical dynamics, molecular dynamics. I want to get the force on acting on each atom. Right? So instead, if I do for each atom, what is the force? If I can somehow get that, but the only problem there was your software packages won't give the total energy. It will give the total energy. They can't give because total energy is not the energy of each atom, but force they will give. So you can train them.
Actually, this is converting this problem to integration problem, that's much more acceptable
Yes.
than doing it in the differential.
Yes.
So tubular will do it. So your Laplacian is going to say do a Fourier transform and get rid of the differential.
Yes.
So differentiation, if you have to solve numerically, the second order differential equation that will be a hell lot of differentiation is a very nasty thing.
Yeah, nasty thing. Yes. That we have already seen when we are doing our simple models too. Even for atoms, we have seen it is numeric. Integration is, yeah. So it's always, so that may answer your question. If you have the functional form for the differentiation too, and if you are trading the differentiation, going back is much easier. And if there are some equations that, some quadrature way you can do that. I mean, as he said, it is much more stable. Here, going this direction of a differential way is highly numerically unstable. And if you do it. So yeah, so again, what I'll do is, it looks like I may not, it looks like, and I'm sure this is going to happen, I cannot give a hands-on, but what I want to, because I have to cover something, little bit, but the whole concept, I mean, what I made my mind while coming here is to just go to simple one-dimensional potential, nothing much. So it will be easy, okay? And what I have done is I got the program also along with me, okay? The program that I have written. I can circulate to you that. So try to at least understand as much as you can, and then we can go, and if you can sort of do the, for one dimension, you don't require any one of us. You can do by yourself. Yeah, Python. So it should be very easy. Okay. So my whole idea here is to go through what I've done. Okay, using your mathematical form as neural network. Okay, function derivative. I mean, for the energy and the derivative both, and then use it for the unknown potential. So that's sort of the idea. So you can do that, and doing an SCF iterative process is not a big deal. I'll show you, and it is very easy. So you can write a Python code by yourself, and then you will get the feel. Okay? Okay? So see, why I'm telling you this is right away. Again, I'll go back to the slides. Is my objective here is to somehow the first model to get the kinetic energy, because right now we have discussed getting kinetic energy is not good. We have to get the functional derivative first and all. But when we started, it was not. And I think I want you to start with the straightforward way to get the energy and then the functional derivative. You realize the problem, then come back. That is always good. Okay, so let's do that. So you will have the energy and the functional derivative. You learned this, okay, everything is fine. Then what? You got the energy, kinetic energy, you got the functional derivative. That's the objective. Then what? What to do with that? My aim is to get a functional form for kinetic energy and its functional derivative. I got it using neural network some way, okay, that is buried in the code. Then what? What I am looking for here? The whole thing is, I don't know in the energy expression, I don't know the functional form of kinetic energy, okay, and I don't know, if I don't know the functional form of kinetic energy, I don't even know the functional form of derivative of functional derivative, okay. Somehow, some way I am getting using neural network. I am doing that. Okay. Once I get, then how I am going to use it? For what I am going to use it? You guys trying to understand my question? So that means if I write, oh, that equation is gone. So if I write my energy, it is here, of course. If I write my energy here, and if you see, this is the one I am getting, okay, and this is the one I am getting, okay, and for simplicity, I am sort of, I have this external potential, I don't have these two, I make it at 0. just for simplicity, as a model system. Okay. Then using this equation, what should I get? What I am looking for? You are not understanding my question? This is the one I am getting using neural network. Don't worry about how I am going to get. It is difficult for you. You may not understand. Let's say some model in computer, I am getting that. Okay? This one. Okay? I have this already defined for me. Simple. I don't know these two. These two are zeros for me. That's a model system. So I just have this simple equation. With this equation, what should I do? This equation. It is your Euler equation, right? Yeah. So you have is equal to the chemical potential. So what should we do with that Euler equation? What are we looking at this density functional theory? What you have to get? You have to get the total energy, right? But along with total energy, what is the other thing that is unknown here? Density. Whatever be the starting density, whatever be the damn starting density, when I do these iterations, I have to get the minimized energy density. No, yeah, it should be R. Yeah, I'll do that. Yeah. Okay. So finally, we have to see whatever functional form you don't know, exchange correlation you don't know, you use machine learning method or some good way where you can construct the mathematical form, you are going to get that. Finally, what you have to solve this Euler equation, that is energy as a function of density. You have to minimize the energy in such a way that you will be getting minimum energy density. The same thing you are doing in Hartree-Fock, right? What you are getting? You are getting the orbitals, the best orbitals. Here you are getting the best density. That density, if you have to put in this equation, you will be getting the lowest energy. Right? That is the ultimate goal. Okay? So let's move forward now. I think I'll just go over it. I'll jump into my things here. This I've explained you before. So, okay. There are semi-local functionals which depend on gradient independence. There are many. I don't want to put more effort. And there are non-local functionals. A lot of people are working on these non-local functionals. I don't know any, to be very frank, honest, I don't know any one of this. These are more complicated equations. Professor Harbola keeps working on this a lot. And requires a lot of understanding and more of intensity there. I don't have much of idea about that. Right now, my life is very simple. I want to only target a simple semi-local functionals here. So if you see, this is the ladder. If I put it on how they look like, I got it from some review paper here. And this is your local functional. This is a semi-local function where it depends on density and gradient of density, and this is your 2-point functionals. These are non-local functionals. Okay. And we are mostly working with local and semi-local as of now. And then this is the standard model. And then finally, from 2012 onwards, then we have this new kind of functionals that are evolved using ANNs. Okay, so we can categorize it in this way. So yeah, I think this more or less, I just copied it from the recent paper, Chemical Review, and the whole motivation for to do this is decreasing the timings, of course. KSDFT, of course, it will go by n cube. Hartree-Fock, you all know how it goes. Into the 4, okay? KSDFT by n cube, okay? That depends on how you deal with interactions, Coulomb interactions. So you can sort of do that. But we are looking for something in this, okay, order of n. Okay, yes. Yeah. The linear scaling method, sir. You have any idea about linear scaling methods? Linear scaling methods. So her question is why there is order of time here. This one I just copied from that paper. But for linear scaling methods, usually the order of time is much more than orbital free. So I'll come up with an answer. Okay, right now we.
Mostly I have seen this scaling with respect to n only. I am not aware of scaling with the order of time. That's why I asked.
Okay. Yeah, both are, I mean, see, linear scaling means anyway it should be linear only, na? That's why the cone sham is getting linearly scaled. But how they are, why there is a difference in time? I'll come back to that. Yeah, that's a good question. I don't have an answer for that, but I mean, if we properly read this, if I properly read and get an answer, it clearly shows. I think it's order of n, and the time is much lower. So that's a motivation.
Is this something to do with refractor or something?
Not sure. I'm sorry. I don't know. Yes. N is number of electrons or number of single orbitals. Yeah. Yes.
The cost is not going to go down. There are linear scaling couple cluster method. That doesn't mean couple cluster will be like costing 90. That's the key factor.
Scaling. What it says that if you have homogeneous function, if you multiply, let's say the coordinates, let's say root lambda. There is a homogeneous function, say any function lambda of x will be lambda to the power n of x. That's the scaling. That will depend on inherent the requirement of the typical methodology what you use, like the linear scaling, couple of mean that
Yeah. I mean, maybe that black line, it should not be that straight then, if that is the case. Okay. But whatever the red line shows, actually, if I'm strictly, it's log n actually, not n, but it's n log n.
another thing is when you say orbital free DFTs, it doesn't mean that all of them will have this type of time. So there are
Yes.
it's the name of family. Not all of them will go this time.
Yeah. I mean,
This is some specific OFDFT will go. Some OFDFT may go like that.
which the black way? I mean, you mean to say? Some
Red line
can go up and down. Yes. That depends on the system and the functionals that you use, of course. Yes, very much. Okay, so let's go into this. So that's what again when I'm doing this, we have tried to map this n of x one dimensional, so nothing much here with TS and functional derivative using the ML method. Then again, once you do that, you have to get the n of x back based on this ML derivative. If we can do that, then our problem is solved. So those are the two things.
second one you are solving Lagrange.
Yes. So we predict. So you map n of x to t and the functional derivative. Use that functional derivative, the ML1, and then take the potential, any potential, and solve the Euler-Lagrange. So the question at that time is, how do we actually model n of x? I mean, what is the way? You have to go for a grid based, or what are the ways? So yeah, so for simplicity, we are considering non-interacting so that we can avoid all the other functionals except external potential.
You figure out density. You are removing Hartree and exchange correlation. That's what you put.
Yes.
They are not there.
Yeah, not that. So that's what I am assuming. Okay. So we have started, because this is the first problem to deal with, and for the students also it's an easier one. We don't have to deal with how we have to get VH and VEXC in any way, okay. But later on what we have done is VH, okay, we got added that, and for VEXC we only added exchange, okay, a simple LDA exchange and a simple exchange, and then we got some results. But to start with, I think this is better for everyone. I mean, if you want to try this, you use a simple model. Now, what model that we used for this? So, okay, so the kinetic energy form is this. So here actually this is positive definite, another form. Now why we are using, I mean at that time I basically I didn't have any idea. We just looked at Burke's papers at 2012 and they started using it. But then I was thinking, I mean usually kinetic energy comes from this, so we can sort of actually so my TS, so that I know is okay. So this is the one that we know usually, and then this is the positive definite one. The way it is written as oh sorry, what I'm missing here, integration. So integration summation yeah, okay. And for the finite systems, we can prove these two are same. Okay, you can work it out. Okay, I don't want to, actually I thought of working it out, but that's not the difficult thing. What you will be getting is, let's say this is equation 1, this is equation 2. So your equation 1 is equation 2. I think then you will be getting this number. Where rho is your summation of pi square pi. So you will be getting this number. 1 is equal to 2 minus when you equate these two. And you can easily show that for finite. Yeah. So for finite systems, this goes to 0. So you can, the way it is understood is, this is your volume integral, because this is dq bar r, if you say, and this is your, okay. So just use your Gauss divergence theorem here. So you will be getting, okay, and then you will be getting, this n is the normal vector, okay. Yeah.
They are equal globally. Locally, they are very, very different. We calculated. Actually, locally, you have to add Laplacian.
Yes.
It has huge fluctuation. Laplacian of the density.
Okay.
Locally, they are totally different.
Okay.
So if you want to say this is 0,
Uh,
I will neglect. Globally, you are right.
yeah. Okay.
But at the end of the day, you have to go for the local. Okay. So the cardinal.
Yeah.
Or let's say integral.
Yeah.
So when you plot that, you have to add this Laplacian also.
Okay. Okay. Okay.
Then if you see the plot of that, too much of fluctuation will come.
Okay. And that's the reason they just for
There are many people exploited that. Fraction of Laplacian of density is added there. Globally, it is not changing any value, but locally, they are giving you totally different results.
okay. So globally, I can put it to 0.
Globally, always equal.
Okay.
Local.
Yeah.
At the end of the day, when you're solving the equation,
You have to add the local part. I'll take care of that. Sure. Okay, so we are for now again model. So we are approximating this with this, and now we have the two equations that we want. Then going back, I mean the corresponding Euler equation is this. Okay, from till here no problem, right? For everyone, simple, right? No issue. Okay. So because we don't have any other potential, we just have external potential and mu. Okay. So now I know what I want. Okay. Then I have to just, the next thing is representation. Now this is the representation that I'm going to take for 1D systems. We have taken, but what I'm asking you, advising you is just take maybe n is equal to 2 electrons or 2 particles. Okay. And they are in different energy levels. These somehow we are thinking that these are not interacting. We should not think that they are interacting. Okay, so you take any one of them, especially better you take this system. It's easy for you, and you can try to solve this problem just to have a working hand. Okay, and then this again copied from Burke's paper. They have used it, so we blindly used it. Nothing else that we have done. And they have used it, I think, maybe for exchange correlation, I don't remember now, but they have used it. Well over 2 or 3 papers they published, they've used this 1D Gaussian potential. This is a simple potential. So is it any difficult for you to program this potential? And you may ask me, sir, what are alpha, beta, and it is there. It is already there in my paper. I can give you that. Okay, you can take that. But why do you want this k? K is equal to 1 to 3. That is fine. But this is one potential I am talking about, right? So what I am asking here is, suppose you want to do a neural network sort of thing, you need many densities and many potentials. So you can sort of change alpha, beta, and gamma, and you can get family of potentials here. That is the reason. But this is a simple potential, right? Any one of you can work in Python, you can easily code this, right? And solve the equation. So we have taken a very simple potential, so you can do that. And once I know, now you may ask, I can give you alpha, beta. Right now I don't have here, but I will give you. I'll provide you with that once I end this lecture. So then you can use that, and you can get the family of potentials. I'll tell you why I'm talking about family of potentials. Okay, but this is one of the potentials here, and then what I have to get here. Finally, my aim is to get density, right? Density should be mapped to kinetic energy. That is where I am right now. Kinetic energy, not derivative of kinetic energy. So what I am going to do, use some numerical, because it's a simple potential. You can use any numerical method to solve this. So any one of you know what numerical methods you can use? There are many actually. You can use many numerical. It's there in literature. Many are there. It's a one-dimensional potential, so it's not that difficult to solve this. Any idea? You have finite difference methods. You have numero methods. These are very well. I mean, the programs are actually there. Yeah. Numero methods. Yeah, it's standard. Yeah. So I advise you take this potential, take this alpha, beta, gammas, and solve a numero equation. You will be getting the eigenstates and E. Okay, and from the eigenstates psi star psi, you can get the density. Right? Till here, everything is okay. Okay. So that's my density in one dimension. Okay, no problem. Now my next question is how to use this density. How should I give it as an input to my neural network? So I have to somehow give. So if this density as a function of x If it is a grid, I can give a grid. People do that. But is it the way to do at the time when we started, or even for a new, if you want to make it something simpler, we will see how we can be in other way other than a grid. But you can use a grid way. Okay. Then whatever way it looks like that, these are your initial densities that you are getting from that. So any one you can take. Let's say this is the one. So finally, when you solve the Euler equation, finally you have to get this back. Okay, that's the aim. So what we have done here is at the time, instead of giving as a grid, because we have good number of points there. So neural network, if you do we have to really? Yes. Yeah, it will come. It will come. This is the input. Not yet come. Machine learning will come. So I have to, for them, what I am designing is each one so that they can go and they compute it. Okay. Yeah, it is coming now. So n of x, yes. Yeah, that this pi I is not the earlier pi I that I showed you. This some basis functions I am expanding it. Yes, fitting only to the density. And fitting in such a way, if I know this pi I's, I have to get the AIs. That, yeah, let's say I know this basis. I'll come to that. I'll show you. Okay, so for this, I've just used the known ones. Okay, these are Hermite polynomials. It worked for me. Okay. So till here everything is fine. Okay. I have my so again you can represent your density in terms of grid points, or you can expand it. Here it's a simple potential. I want to expand it. Now one thing I want to set it right. There were papers in which, because this kinetic energy is non-quadratic, it's not easy when you use orbitals as your normal SCF calculations. So it will never work properly. You have to, there should be other way. You cannot expand it in terms of orbitals and do a minimization. That is always a problem. So people tried to solve this Euler equation mostly based on grid methods, but orbitals did not work, especially when we take these Gaussian orbitals and all. It did not work for people. I am just telling you, either no problem, here no issue. You can do it. Yeah.
Here you are doing psi star psi itself. This kind of density is expanded.
Once I know the density, I am just expanding with the known functions here. Okay, and it is not that difficult because I have given the form of it. Okay, what you have to do?
This function can be anything, like this doesn't have to be.
No, it's up to you. Okay, for me, Hermite worked better. I used it. Okay, now it is these are your A and P are your variation parameters. You can vary them and you can optimize them. Okay, and how will you optimize this? You go to any curve fitting tool in Python, you can optimize. Understand? Any curve fitting tool, you can optimize. Once you have optimized, then what you have. So the ultimate goal for me, why I am doing all this is, instead of n of x as a grid, I will be giving this finite AIs as my input, as a representation to the density. No, orthonormality is there. Yes. I used what tool? Minimization tool in SciPy. What minimization tool I used? I used 2 or 3 actually. एक तो Bayesian hopping भी use किया है. I mean, I have used Bayesian hopping. I have used non-linear regression methods. I have compared it with many, but more or less it is coming to the same thing. Okay, SciPy has many optimization. Curve fitting hai, minimize hai. You have curve fitting, you have minimize. and you have something like heuristic tools also. So you can use that from SciPy. Okay, you know SciPy, right? Nahin. Okay, so Python comes with its own libraries. Like one is NumPy and one is SciPy. Okay, and see that's why we see earlier people used to do in Fortran and all. So it used to be a bit complicated. They used to use linear algebra tools. In Python, why I suggest, I think you guys, I mean, you guys are teaching Python, right? In first year, we have also introduced Python because it becomes so easy in life to use these tools. Okay, so please use again. I mean that's what I heard. I talked to many faculty around, and people say interactive Python, IPython. Okay, with Jupyter Notebook, I think that will be much easier. Everything is there in that. So if you learn that, and hardly it will take a week for you to learn, and doing this will be much easier. If not, you write the code for optimizing this, it will take a long time. Yeah, you can do that, of course. That will be.
Libraries there, they will do it.
That's the bad practice. You never learn.
So this year in MSc, that's what I taught. I mean, you were not there. Now we changed and we put a computational course. So I told them, don't use any libraries and write the code.
Like I'm telling, I do numerical method, write the code.
Yeah, write the code. Don't use package. Yeah.
So this is something that you go write any numerical package and show. Like you have learned the orbital shapes. S orbital is like this, E is like this. To solve Schrodinger equation numerically and show me that do the plot, GNU or whatever plot. Show me that you are getting exactly the same picture sorted. Blindly, you have been learning from your school days that S looks like that, P looks like that. You have hydrogen atom. Analytically, you have solved analytical programs, so you know the functional form. You plot it. Another way, in addition to that, you solve the problem numerically. It's just a very simple problem. Numerically, you solve the problem and show the result you plotted and show that the typical orbitals were same picture from one. It's a very good exercise. You learn photons, those pictures are
Next time.
Yeah, I think, yeah.
It's very simple, very simple. Maybe 10-15 lines.
A numero method, and I think these optimization problems, I think they can do it without a package. I think last time I made them use the package, but I think, yeah, in the MSc. Yeah. I think this, if you can write, see, once you know using package, I mean, at least you will understand what the package is doing. So that's what sir is telling. And regression, I think simple regressions, it's very easy, but still Python has a package for everything. So, but there is no point in doing that. Even to that extent, this heuristic method like a Bayesian hopping, simulated annealing, all that has packages. Where I was a student, I was writing my own programs there. So always, I mean, just to get an understanding, once you have the feel, then you can use the program. I mean, the package, no problem. But once you should have the feel. Yeah. 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 So then once that is done, then okay, then what is the expression now? So I'm not showing that the picture that I showed you before, but somehow we have how it is mapped finally. So let's put the picture directly on it. Okay. What this says is, if you see the brackets here, this is nested, right? So, and that's what is really happening when I drew the picture on the board before, right? If you remember it, let's say I have only 3, okay? Yes, I'll tell you in an easier way. So I have one there. Let's say something like this is my network. Okay, and it is doing, okay, that is the network. Okay, so what it's showing is here, this summation, okay, that is inside these three. Okay, that means you have your A's. Remember how did I expanded my density? Right? Of course, you may ask, sir, why you have A, I, and J? Because here I am referring to the network layer 2, so I have one more subscript. Other than that, AI gives number of A's that are used to represent this density. Yeah, yeah.
Like you have only one connection, one three connection also.
One, yeah.
And all such are.
Yes. Okay. All connections will be there. So that's what it is showing exactly. It is translating to that formula. If you see, these AIs are here. Okay. This WJK 0, 1. So this is my 0, this is 1, and this is WJK. So JK. Okay. And then, as we discussed before, this is my bias. Okay. And then I have this kind of activation function that I have put. Okay. Earlier I showed what sort of activation function I take. Activation function is from linear to non-linear, sigmoid. We use sigmoid here. Okay. And then, of course, come to the next one. So that is WKL12, that is these two, and then do the same thing again, because this whole sum is here. This summation here, this whole summation here comes to this three. So then you multiply that. I mean, you do the activation function AF and multiply with the respective weights to get the next layer. This is your second layer. That means 1, 2. Okay, and then do the same thing again, and finally you sum everything to get your output. Difficult? It's just a nested addition, right? The only problem you will have to learn this technique is writing this is very simple, coding this is very simple. Okay. Now you may ask me, sir, how I am going to get the differentiation of this, the functional derivative of this. That also I will show you. You can get it easily. But the problem is not that. The problem is how I am going to supervise this. Okay, that is where I have to. I mean, supervise means then I should have a that I cannot write by my hand. I mean, it becomes difficult because these weights will be huge. Okay, so everybody has some understanding how this is reflecting to that. Okay, so once that is done, then
So the W is a kind of row vector, A is a column vector. Then you take dot product, scalar product of these two.
I think, yeah.
You can
Yeah. So what I advise you guys is to, and what, because he raised this point, again I remember something. You go to again, sir, do I really have to learn neural networks? Now that's a question. See, if you are a computational chemist, at some point, I think number of papers that are coming out are huge. So I advise you to learn it. Now, how to start working with this? So there is a beautiful book. Again, I forgot the name. Fundamentals of Neural Network. It's a big book. Just write it down. I will send you again. I don't remember now, getting confused, but I'll send you the name. What it gives you is, because he raised this question, instead of me writing, he will put everything in terms of matrices. Okay, weight matrix and the coefficient matrix. It becomes very easy and he will show you properly. to do that, and that will be much easier. Yes, you are reading a big book, but it won't take that that amount of time for you to understand it. Okay, I learned it from there only. I and Arup both learned it from there. I'll send you the book. It's Fundamentals of Neural Network. It's a big blue book, big one. It's like your A4 sheet, na? That size book. Okay, I'll send it to you, and you try to learn from that. Then it will be much easier. Okay, there this matrix components usually come, but for you to understand, I mean, to start with, this is fine. So with the network itself, implicitly you can get the functional derivative. Okay, so you are getting Tj, ML, and also the functional derivative. Both you can get from the network itself. Okay, and then this can be easily shown as your basis function pi I. Not that difficult. Okay, if you do this, this is not that difficult. This can be easily shown, so that right now you have a way to get both the energy and the derivative. Again, I am telling you, this is the model problem that I am going to give you. This may not work. This will not work actually, because you are getting both. You are trying to get the energy, and from there you are differentiating to get the functional derivative. Okay, and then some way you are, I mean, you are supervising it with the energy that you have. So how you are doing that? I didn't show that. Okay, yeah, I mean, everything is here, of course. Then I will directly take you first through to some results. Okay, so if you see, let me. So you have Ts, ML, right? That you have got from there, right? And then you have Ts. That is your reference Ts, right? It can be supervised. No problem. Now, from that equation you have right? This is the one you have. Now, this you need, right? So, this you have already with you. What is this? If you know this is your reference, right? What is this? Mu. What is mu? What is mu? Chemical potential, array. Chemical potential, right? So, how do we get chemical potential? Yeah, it is dE over dN. Okay? Then what we have assumed, there could be questions here, we assumed it as E by N. Total energy divided by number of particles for this problem. Okay? So, in that way, I can get this reference. Now, I have my reference kinetic energy. I have my reference, so let me write it down. N is the number of particles. Okay? So just to make sure, nothing fancy, very simple, to make it very simple, I have all this data. Now I just have to run. Now where is the problem? Sir, you have given me everything. You have got the ML version. You have got the real version, I mean the reference values. Now where are we stuck here? We have to take the error between these two. That is ML minus the real version. Okay, and optimize my weights. I have to optimize. So because I don't know what are weights, so to begin this algorithm, what people do is they will give some random weights. They start with some random weights, right? So usually we take everything in term, I mean, more or less this, everything should be scaled here. That is important. If you have your inputs, these should be scaled. because there cannot be any big values just like that. These should be scaled. Your input values should be scaled, okay, between 0 and 1 or so, and then only we can perform this. That will be a yes.
Here we have two layers in between the input and output. Is it because we are approximating this kinetic energy constant second order?
No. That has nothing to do with two layers. Okay, no, don't even think in that way that just because it is second order derivative we have two layers. That has no, functional form has nothing to do with, these are completely empirical. Completely empirical. Okay, I am just taking because I am writing the formula in that way. If I remove one of the nodes, I will just remove one of the hidden, I will remove. Now you may say which is right. Which is right is the problem that we have to do by trial and error. I cannot say. For us, we got it with two layers. Now, no, I mean, yeah, there are issues also. If you increase the layers, it's like, I'll tell you, it's like your curve fitting problem only. Okay, let's say you have some curve fitting. Okay, let's say you have points like this. Some points. Okay, so you can put some polynomial. Let's say n is equal to 2, 4, some polynomial equation you put. Y is equal to w0 plus w1x plus w2x squared, some polynomial, right? Now you may say, sir, shall I go up to w2x square? Shall I go beyond that? If you go beyond that, you will be getting an excellent result. The problem is, when you want to define, I mean, when you want to see the point in between, there will be huge amount of flux. It's called overfitting problem. Okay, so that's why overfitting comes a lot in neural networks. It's a fitting. I mean, the whole approach that I am showing you is just fitting. Okay, so overfitting comes. So that's why you have to sit down. There, the student effort is must. Have to design how many layers I need to have, and in each layer, how many nodes I should have. How many nodes means this circles how many. These as my empirical. Okay, once I know that, once I optimized it, I have to see. Then you may ask me, what is a way for me to check whether some things are overfitting or not. Okay, then there is a proper learning curve that I will show you. Okay, with the this whole thing that you are doing when I have this subscript j is for jth potential. In that way, you will have many potentials. So you will be so many potentials simultaneously you are giving and optimizing the weights for a family. You remember I told you family of potentials? What do you mean by family of potentials? That alpha, beta, gamma that I have before. So let me go back. Yeah. Okay. The alpha, beta, gamma that I have, these can be varied to get a family. Okay. So every family, every member of the family will have its own density. Right? And every density can be expanded and can be represented in a neural network. So every density will have its own kinetic energy. So there is a family of this. That I cannot do it with one, right? If I want to train these W's, so go front again. So no significance. The only significance is to give some flexibility so that I can create a family. That's all. There is nothing else. And to make it very simple, we have given one in the exponent, one as a coefficient, and one as a standard deviation term. Okay? So there is no significance as such. Okay, but that will give you a family, because that's the thing in neural networks, right? You need family to train. One thing cannot be trained, because finally what you are doing, what is the ultimate goal? Once I trained this family, somewhere around this family I have the new one. I don't have to train. I can get the energy and the derivative easily. Understood? Understood? Okay. So finally what we are doing, so the challenge here is, I have to somehow dig into the weights and get the weight matrix, okay, optimized, and that's where is the challenge. And uh, 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 one of the method that you see, again you go, I'll give you that book, and that book has how to optimize these weights by hand. You don't have to go to any fancy books, okay. uh, uh, you do it by hand, it will be much easier. And what it says is, it will use what we call a steepest descent method, okay. So what it will do is a sort of what we call as a back propagation method, okay. This word is used a lot in the literature too, so it's good for you to know it. Back propagation. So you are coming back to optimize the parameters. Why you are coming back? Because you have the reference here. So you slowly optimize these weights, then using this you optimize this, you optimize. That's how you come back. Okay? These things are well known. Okay? It is a simple gradient descent method you can use, and you can optimize this. In that book it is properly given and it is very easy to read. Okay, right away I will search for the book, I will send it to Soman and he will circulate it to you. Okay, please, if you have a chance, buy that. It's always good because it gives you the Python code also along with that. Okay, so you don't have to, to get a motivation, it's always good to have something reference for you. So you can optimize these parameters. Once you are optimized, you are done. You are done for the day, because you can use this and get the density, right? And that's my ultimate job. Once I have this, I can use this and get the density. So let's see how I'm going to get that. So I'll just show you some results. Don't worry, don't put so much effort in understanding this, but results are good. That's okay. Not that great. I'll show you the problems that actually comes. This is my predicted and exact kinetic energies. I'm trying to see how far they are good, and then these are my predicted, and so that's the problem when sir was telling, as soon as you get the derivatives, it mismatches a lot. I mean, that you can see here, it's not good. But if you can train directly the derivative, this problem that I will show you soon. That is a problem here, and why I explicitly want to show you the figure sets. It's an okay match. We can quantify it and do all that. But can I use this and get my density back? That is the ultimate goal. Can I do that? Yes. That's some abbreviation. Don't worry about it. Some abbreviations in which U is when two electrons or two particles non-interacting, they are standing like this. P means when one part, especially for 3 it will come, one particle is on the upper state, two particles are taking the ground state. Okay, that's the abbreviation that we use. Finally everything is non-interacting. That's an assumption. So don't, no. I mean, yeah, you can say spin particles, but still my assumption is non-interacting. That's why I don't want to use spin. As soon as I use spin, you will see. This is a problem. When I made a mistake here, I know. When I say this, where is it? When I showed this, this is not a good way. Instead, actually, Arup made his slide in which he just put two dots instead of these arrows. That is better. It will create a lot of confusion and say you are saying non-interacting and you are saying spin again, and why this confusion should not come. So don't use these arrows as such. This is wrong actually. You put two dots. No. These are not fermions, huh? These are just particles, just some particles. Yeah. If you, because that, yeah. Okay. So these are my okay. Somehow this red line is my machine learned functional derivative, and what I want to do is I want to use this and get my density back. That is my ultimate goal. Can I do that or not? That's the thing. So how I am going to do? So we'll use this. So this is my Lagrangian. So everybody is okay with this, right? Right. So this is the equation where I'm going to get the new density from my old some learning parameter with the Lagrangian as a function of n. So that is the way it is defined, right? This is what I'm taking for ML. Okay, and doing this again is a very simple thing for you. Why I'm putting all the effort here to do line by line? Because you can just copy this and code it. Not a difficult thing. Why? Because if you see, these are my coefficients, right? Coefficient times the orbitals, finally, times this, right? No issue till here. Same n I am writing in this way. Okay, so I don't need to optimize on orbitals. Orbitals are already there. Only thing I have to optimize is my coefficients. That's all, right? Simple. I'll just wait for some time if you want to take it. And these I said when sir asked me, these are orthonormal orbitals, so you can get A's.
Functional derivative and analytical function. You are using
No. This is my energy. I am not taking the functional derivative from here. What I am doing is implicitly I am differentiating that with the weights. That's the yeah. So that's how I am getting the functional derivative.
So what I am telling, say, when you write that the first line, so that n there, whether it is n old or n new, because you have to do the iteration, isn't it?
This is my n old. N old. Should be n old only, na? N this is n old minus this should be n old only. Why? Any?
That's what I'm asking.
No, it is n old only. Yeah.
So you calculate with the say base
Yeah.
density.
Yes.
And then get the new one, put the new one
Yeah.
back, and iterate.
And do the iterations. Yeah. Hmm.
These are your orbitals, but these are some functions fitting density, not orbitals, right?
These are, as I told, these are Hermite functions. Okay, and we can easily remove them, na? Because these are orthonormal. So we can just write everything in terms of A's.
Remember, if it is orbital, it should be orbital star, orbital
Yes,
sum
yes,
of that. That would be your density. Here you can see the density is expanded in these basis functions. So it's not pi mod square, it is pi.
Okay?
Some kind of density.
Yes. Huh. Let me go back.
Yeah, here.
Hmm.
Like you can see that sigmoid can help us model this periodic function, right? Whereas if you tell you probably get piecewise linear function, but we can model this way. Like that's an infusion is there. Like I want to know why sigmoid.
Why sigmoid? See, sigmoid is easier for me to differentiate. ReLU, yeah, you can do ReLU also. I mean, you can use even to that extent. Tan H is also not a problem.
No, even linear function. It's linear activation function is also used. Linear functions are also also used as this activation function. Sigma gives why these functions are used at the very last place. Suppose you are having some ALM model, it is giving some kind of output, and then you want to generate your known output. So if they are far removed, obviously everything will get disturbed. So you want to suppress it so that whatever values are coming, it is getting cut off somehow. So that it comes, there must be some kind of say semblance with the actual.
No, that semblance.
What you are doing, you have some input, you are putting arbitrarily some weights and biases with proper connections and write the formula what you are taking. So you are generating some kind of, let's say, TS or del TS table. But you already know it's a solvable problem. You already know the actual TS and del TS table. So you are comparing this output coming from your ANN and the output what you know analytically. Okay. So what is the difference? So this difference you have to minimize. Okay. Or let's say del error del is should be C. But if it is not there, you try to minimize that. You go back, change your weights and the biases, come back and check it. Now doing this, if they are originally there are removed, obviously you will never be able to do this. Only if they are very close and your activation function like sigma is doing that. So it is bringing that result from ANN very close to the known output, and that's why.
No, but when you, yeah, no, when he used word semblance, I mean, see, suppose let's say you don't use any function there, then what will happen? It's a linear one, na? See, you have weights times the inputs plus some bias summation. So you are only linearly, but how do you know this? Is the row connected to T linearly? Is the row connected to kinetic energy linearly? No, it's not. Nothing is linear there. So we have to somehow in this artificial model, we have to give that non-linearity. So non-linearity, as you said, yes, it can be given in many different ways. Yeah.
So, like, let's say X square is a smooth curve. Whereas if we try to fit multiple linear models in a piecewise manner to an X square, then it will be like lesser smooth curve. So, using a value kind of function, I thought we might end up getting a non-smooth curve. Or sigma function is giving a smooth curve. But when I'm trying to imagine the use case of sigma, like I can only imagine periodic, like fitting into a periodic function. But from the results, it didn't look like that. So, I wanted to know, like, how to decide the activation function. Probably this is a question we can ask to Google also, but just like not a fast thinker.
No, I understood your question. I mean, see, my whole intention here is to give a simpler function. I know. Where are you? Why can't we use ReLU and see how it works? That's the basic question, right? Yeah.
When we do model fitting, like we try to go through multiple iterations, right? So I wanted to know, like, if ReLU didn't work out.
No. I did not, to be honest, I did not use ReLU. Okay, I used only tan H and this one, and they work the same for me.
I never used tan H, so I couldn't imagine the function of tan H.
No, tan hyperbolic only I use, but ReLU is the one that we can see. Of course, we can see. That's a good thing. But when I'm throwing the problem open, these are the things that you can try and see how things work. I did not do as of now. Yeah.
So like the weights, biases, how many hidden layers, what you will take, you have to do trial and error. That is the major. And the activation function also, there is a zoo of activation function. Sigmoid is easier to handle, that's why it is. I myself have taken linear. It is beautiful. Just linear.
No, but you might be knowing now why sigmoid, because you take the differentiation of x with respect to x, you will know why it is. You can write in terms of function only, like your exponential. You can write.
You try and you see how many iterations does it take to get your machine learned quantity output and your own analytical original output very close to each other. If you see the sigmoid gives this less number of such iterations to minimize the error, so that's sigmoid. If it's a linear, it's minimize your linear. This also nothing. Because once you treat this, the original aim is to treat the DNN model. After that, any arbitrary stuff belonging to a similar family, to put it there, you get the result without doing that.
Yes, we can guide to choose this better functions.
Which one?
You are saying we can take different functions, try to fit it.
No, whatever.
Your main aim is to
Guess the better
minimize the error in minimum number of
No, I mean, to guide you, people have worked all this. That's why few functions are coming in open, right? Like sigmoid, tanh, ReLU. There are few. I mean, there could be a family of functions, but usually people use this. Okay, so don't worry that you may have an ocean of things that you have to experiment with. Not much. Very popular. Yeah. And to that extent, even the number of layers that I am showing, the number of these variable hyper variables that we have, number of layers and number of nodes. These also, with some intuition, with some practice, you more or less you can construct 15, 20 nodes for these kind of problems. Okay, and then 2 layers or 3 layers you can construct. The only thing is you have to sort of, some effort has to be put in to see if there is no overfitting. And that you have to check. But
suppose you are doing trial and error, you are getting weights, biases, activation function, etc. You will get some kind of feeling. In the next problem, you will not require that much of time. Okay, you know what are the types of weights and biases and the activation functions you should take, so that minimum amount of time you get that feeling you.
okay. Yeah, I mean. Want to say something? Yes, please.
Yes. Because functional maps a set of functions with a set of numbers. Later I remember if you say function of a function, it also maps one set of functions with another set of functions. Sir, I want to know, like, given this neural network form which you represented, which is a function of a function, right? But we still call that as a functional. So I wanted to know a relationship between how this can be treated as an integral of g of x comma f of x. Like, let's say, why do you say it is a function of a function? I think across machine learning literature, I see that neural networks are called as functional forms of classical machine learning models. And even in
I think that word is a bit arbitrary.
No.
Yeah.
That's wrong literature. Mathematically.
No, I mean let's say I see if you take in this way, let's say you have row of R and you are getting T. T is a functional of row, right? T is output. T is a functional of row. But if you, for example, not even T. Let's say you take some potential V. V is a functional of row. But then when you calculate V, it's a function of R only. If that is the case, you take the function of R. Yes, when I say functional, or see, that's why you have to sort of a many-to-many mapping, right? It's a many-to-many mapping. So this depends on all of this. Every row here. And this row is calculated every R. I hope that is making sense. I mean, because this question has come to a referee also. Recently he was asking us, okay, how, I mean, because you are getting into that direction, I want to just raise it. Suppose, let's say this is your output. These are my inputs. Let's say I change these two. Let's say I am giving this 1, 2, 3. Now I am changing 1 to 2 and 2 to 1. What should happen to my output? Real sense, it should not change. It should be permutationally invariant, this one. But will this really happen? Because once I change these two, the weights, according to the weights, everything is changing for me. Right? So what the reviewer keeps asking us is, did you make this permutation? There is a way to do that. Finally it has to come to a level when these one, no matter which, you can give 3 on the top, 1 on the 2, which way you give, irrespective of the sequence, you should get the same energy out, same output.
You are calculating the value of the function for a different set of values. What do you get? You have a set of numbers, give another set of numbers. You know, so where is the function? I can see only numbers. It is exactly like this. Whatever it is. I can see the function of a function. No. At the level of operation, you are seeing. But actually, so suppose I have sine as a function of it. For a given x, I am getting sine. I ask, let's say I write a program and I calculate sine x as a function. What do I get? I get one set of numbers, I get another set of numbers. So where is the function? I see only numbers. Numbers are functions of product.
Yes, sir, I understood whatever you explained earlier also. You gave an example also. So I understood the definition of functional and function. So I wanted to know how this can be expressed in a functional form, because people
Numerically you cannot do. Numerically you cannot do.
Okay. Because
So I have been telling you, you have to do a card picking. I have been telling you, card picking is equal to that. But at the end of the day, you want to be the you don't need anything else. What does it matter if you get at the end of the day density at different points as set of numbers? That's what you want. Energy, only one number. What is the form of the energy function? You don't care.
Yeah, it's the same question that somebody was asking me, do you need an analytical form for this? Finally, you have to get these numbers, proper numbers. Then you're done. Okay? Yeah.
So like any computation, whatever you are doing, that is your main aim. Generate numbers. You keep all your algebra, say differential calculus, integral calculus, somewhere else. At the end of the day, you are doing numerical differentiation, integration, solution of differential equation. Everything you are doing numerical. Okay, you are doing Newton-Raphson, you are doing Frank-Nicolson, whatever you are doing, they are not the actual calculus. They are something else. Okay, so that's what I told you. If you ask a computer what is a plus b whole square, it will never be able to tell you it is a square plus b. Give some value of a, some value of b, it will give you a number.
See, there is one paper also. Again, it is on my desktop only. How you physically interpret this neural networks, because neural network is a numerical method. Okay, though they are something like physics informed and all nowadays, but usually what is the physics behind it? That itself is a tricky one. Okay, it's all playing with numbers, nothing else. And there is a PRL paper. I can give it to you. You can circulate because they can read it. Okay, just to have an idea. Because what is the underlying physics behind that? Because usually neural networks, I think in engineering, if you are from CS and all, I think they are used for image processing. Mostly it is. Okay. Yeah. Anyway, let's move. Any questions here? Okay. So so you can get this finally. Let me just jump into this. So these things that you can get. So why I'm showing explicitly, you can write it down and code it. Okay, you don't need any function here. Just do the iterations, and you will be getting your AI news, your new densities. Once you get the density, just use the same Hermannite functions, multiply, and get the form of the density. So that's what we have got here. If you see, and I don't want to even quantify this, but this is the result. So finally, that's what we want to get. So what I want to show you here, it may be difficult for you to see. This black one is the real one. Just a minute. The initial one, and this this is my target. Target means the actual one, the blue one that I showed in the beginning. This black one is the initial one. Initial means some density I am taking. Okay, it is somewhere. This red one is after doing these iterations, it is coming here and stopping. Okay, so you can conclude whether it is a good fit or not mathematically, because for a simple system we want something very accurate. Okay, it cannot just be something like this. Okay, so but still you can get these pictures. You can do the computation. You can write the code. You can get these pictures. Have a feel of it. Okay, because once we have come to here, we were okay. We have tried many other things, many other optimism. Finally, no matter what we do, we are getting these kind of densities. Nothing much. Yes, red one is my ML density that way I'm getting. This. We tried, sir. No, that we tried hidden layers. We fiddled with it as much as we can, but we haven't seen. And the best ones I'm showing you actually. Yeah. Maybe. I mean, I can leave it open to the students. You can try this, of course. You can. There's so many variables here inputting now. So, so you don't even know. And when he says activation function, you can do a lot of things and see.
If you have 3 parameters, it will fit in anything.
Yeah, but you have many parameters here, so that you can try. It's an open question. Okay, but then what I believe is with this, I am asking you guys to sit down and do this simple Python coding and try to get this, because there is no additional things. And what I am going to do it for you is this neural network part. You don't do whatever I have F90 code. Okay, Fortran 90 code I'll give you. So what you have to do, you take some density, do the optimization, simple optimization, so that this one, and get the density. So one feel will come that I am starting from some density that is not the density that I know, some arbitrary density, whether I am getting close to the density or not. That feel will come. So I am going to give you the code, F90 code, that will give you what F90 code will give you. It will give you neural network energies and neural network functional derivatives. So somehow you put it in your Python and run it. Understood? So you take some arbitrary density, you have this neural network things that will help you. You don't have to do any neural network. What you do is, so then what you'll have a feel, okay, fine, I start from some density, I have this neural network, somehow it is predicted, I do these iterations, I end up somewhere. Okay? That's what is, I mean, I thought of giving you and asking you to do in the lab, but I think it won't happen now. It's already time. Yeah, but I think I will send it to you if, I think, yeah. So 4 things I remind, you remind me, I have to send you, then you please circulate it to them. So if whoever is interested, they can work on it and you can directly email me. Okay? So yeah, and so I have things, a lot of things again, what we have done now here. So, yeah, I have done, not this is a model system, but gold clusters I have done, yeah, I have done that. For gold clusters, yes, I have made ML potentials for gold. No. That is completely different what I have done. There, what I have done is, I've got the total energy. Now, you may ask me, total energy, but how each atom, because each atom I took, okay, that is a little bit of something away. What we have done is, a neural network gives, don't give the atom in the space. What it gives is the surrounding environment. So I made a functions in such a way that it gives a surrounding. Why I have to do that? Because I don't want my input should be translationally and rotationally in a way. It should be translational because my energy should not shift wherever I do that. So for that I made some functions, Gaussian type of functions, e raised to the power of minus alpha rij whole square, in such a way that I have these kind of functions that are my inputs. Okay, then I will be getting energy. Now these are atomic inputs. For each atom I need many, so I'll be getting atomic energy, but the only problem there is I don't have atomic energies in the DFT package if I use. So what I will do, so I'll take the total E and I'll divide it by N. I'll just put it so that as much as possible you learn. So that is that the problem is when we in DFT calculation you have total E if it is force. So that's why I do learning of both the same way here. Total energy I learn and also the total, not the total force. Force is individual for each atom. I can get it from my my output, Gaussian output. I can get force on each atom. So that I will do the proper matching.
There is no force acting on the
No, equilibrium geometry, we take any geometry. If it is equilibrium geometry, then it's very difficult because force is zero. Yeah, it's gone. But we take arbitrarily, we give, see, inputs means what? Input means you arbitrarily, you give from dynamics whatever states you are getting. Then I train that. So I am taking the force factor. Then I will be getting what? Energies anyway is there, total energy, but I am getting the forces. So once I have force, I can do classical molecular dynamics simulation. Once I have my potential, I can do a classical molecular dynamics simulation. Then I can get the potential energy, complete potential energy. Then I can get my global minimums, whatever I want, I can get from there. So that's what I have done earlier. I was getting, but again, human factor is huge there. I have to put a lot of effort. Computationally, it is okay because if I just use a CPMD, sorry, ab initio MD, it will take a long time. You cannot explore. Professor from Pune, what is his name? I forgot. But he does a lot of Kohn-Sham DFT calculations. No, not I said Pune. University of Pune. Gadre. Professor Gadre, yeah. So they do a lot. So we used to refer to his papers a lot. But then, because they are mostly interested in melting and all, melting transitions and all that. So we could easily get that. But they used to do with KSDFT. And that's huge.
It's a physical process, you don't have any time. You have to break a bond.
Then I'm done. I'm finished. I don't have to. Physical processes, okay. No issue. So,
And how large is the cluster?
we went up to, we went easily for energy calculation. I went up to 923. But the problem is, these are all mostly as soon as you you increase the size of the cluster, it will be morely icosahedron. So no problem. But as soon as you come to smaller clusters, you have quantum effects and all. And gold has many other relativistic effects and all that. So it will create problems. So up to 147 we could get. So our even till now, if you see the literature, the neural network, because nobody can do 147. You cannot use attention or a Gupta potential. We have to do ab initio. Then only machine learning can do. So there we have conquered it, no problem. But above that, no. Other than that, we can do. You can put one more layer and all. But then you can't do a dynamics on it.
Because there is nothing to compare with.
Yeah, 147. Somebody has done it. Then, but sir, people come with all weird structures and all, but some weird potentials they use and they compare. And Professor Goidkar, so he argued with me a lot in one of the conference in Switzerland. He said, "Sir, your PBE, nothing is." So I said, "I am matching with experiment." Anyway, he is not, no, DFT won't work. You have to use classical potentials as you go into. He directly told me. Now it's over. What will I argue with him? So around 500 and all, it will be all icosahedral. DFT won't work at all. So you have to use classical. I stopped it.